So, hello everyone. Thank you for allowing me to participate in this event. I'm Nesrine. I'm a PhD student in LS2N in Central Nantes. I currently work with Olivier Carmorgan, for those who know him. And I'm going to present to you a part of my work, which I call pure image-based approaches for autonomous underwater vehicle docking. All right. So, as most of you may know, the act of docking is all about the recovery of your unmanned underwater vehicle after typically the end of its given mission, whether it is supervision or intervention or anything like that. So it is typically teleoperated in the industry cases with the help of talented ROV pilots, And as you can see, for example, on the image on the right, we have mostly what we call a launch and recovery system that controls the launching of a tender management system with a docking station. And the recovery of the AUV is done this way. The autonomous solutions are mainly explored in research and also mainly revolving around docking into fixed seabed docking stations. So the case on the right is rarely explored in an autonomous fashion. So underwater vehicle docking is mainly divided in two parts. We have the homing phase, several hundred of meters away from the docking station, where the autonomous vehicle or remotely operated vehicle has completed its mission and is seeking to go back to the docking station. So generally, this phase is mostly acoustic-based and doesn't require much precision. It just basically has to end roughly in front of the docking station. And then we have the terminal docking phase, which is mostly vision-based, and it's basically the most arduous and sensitive one because the precision is needed here. All right, and it's the part where the AUV is recovered, basically. So in research, we can see that the divide is mostly there. So the homing phase is mostly acoustic and the docking phase is mostly visual. Sometimes you can have hybrid approaches. Sometimes we can have purely acoustic or LiDAR-based guidance, but this is the main framework we notice in research. And you can notice as well that it's mostly for fixed docking stations on the seabed. But also dynamic docking scenarios have been explored. We have had some very interesting work that explored the adaptation of another robot as the docking station, or even some kind of claw recovery systems. All of these are very interesting, but they mostly remain in the research and development phases, and they are not yet industry available. So for the industrial case, so far the only work that has been accomplished for the industrial setup and also validated experimentally is this one, which is actually very impressive. And it has been using a very sensitive position-based visual framework, which has, of course, its limitation. It's all about how you reconstruct 3D positioning based on images, and we're going to try to explore the alternative to that, or on a very similar setup. So we have, for visual servoing, two different ways. We have what we call position-based, which has been used almost exclusively in research for autonomous docking, which requires the computation of the pose from the image, and then the control is done in the Cartesian space. Of course, it is very intuitive, allows for sensor fusion, and the behavior is actually interpretable in 3D space. But knowing all the position computation problems, it remains sensitive to camera calibrations, target 3D model, and all the pose estimation issues. So another side that has been very rarely explored for docking, and pretty much not really validated experimentally, is the image-based visual servoing. The first type of visual servoing we think of when we hear the word visual servoing. It's all about matching the visual features with the desired visual feature position. So basically, it's kind of very roughly match the points. So it is directly in the image space, doesn't require all the 3D pose reconstructions, doesn't require that much precise camera calibration, and always makes sure the target is visible. But unfortunately, it is very sensitive to gain tuning, is very sensitive to error, especially as we get closer to the target. It is also camera only, so doesn't benefit from data fusion. And of course, sometimes the trajectories are not feasible or optimal in 3D space. So in my PhD, I decided to give IBVS, like pure IBVS, a chance for docking scenarios. And I'm gonna present what I mostly did up to now. So another core idea I'd like to transmit that's gonna be useful is the visual memory navigation. So basically, it has been mostly used for wheeled and humanoid robots. It's some kind of biomimetism, like by kind of mimicking humans. Basically, going to a place and then remembering how you got there. So what you do is you teleoperate your robot down a wanted path. You record a sequence of images, and then of course there's the whole image processing thing where you extract the features and all. And then in your autonomous run, you're gonna make sure to match the current image with the closest key point. And then from key points to key points, you get where you wanted to go by the end. So it's a concept we found very interesting and we wanted to use for our work. Also for visual servoing, it kind of widens the basin of attraction so it remains better to have a trajectory than to have like just a final set point. So this work has been published and presented in i3 Oceans 2025 in Brest. So it's all about recording with teleoperation a sequence of desired features, positions. Then our IBVS controller, with the help of low-level controller, typically a PID, for example, will try to recreate that sequence. It has the advantages of IBVS, so image only, no 3D reconstruction or other sensors. It's adapted to dynamic docking, like for the industrial case, due to adding such things as feed-forward. And of course, it accepts large starting errors, and it's fast to deploy because it's very easy to have a teleoperated sequence of images. To keep the math very simple, basically it's heavily based on the motion tracking controller from François Chaumet, which is quite easy to use. So it's very classic visual-servoing. We have the instruction matrix that kind of maps the feature evolution to the robot velocity. And we have, of course, the feed-forward, which here is an estimate of the TMS motion and the feed-forward of the feature variation. And then it's a very classic proportional controller. So I won't show the result here because the presentation is still a bit long. We validated it in simulation for now using Blue-ROV2 model in Gazebo Garden and ROS2 Humble. And we simulated a moving cage, like for the industrial case. As you can see here, we have a visual trajectory with in blue where the features, where the wanted feature are, and in red where you want them to be in the end. So basically, it proved to be successful. We tried it in a few scenarios: calm waters, then a moving TMS, then adding some light lateral current. The IBVS classic structure worked across all scenarios with pretty much no tuning between scenarios, of course. And the behavior was actually very satisfying and visually convergent. The limitation is the performance kind of degraded with stronger currents, and also the convergence was a bit slow, especially given disturbances. So we thought of actually using adaptive IBVS. So the next step that we actually submitted in I3E advances in intelligent mechatronics is to basically achieve that adaptive IBVS by keeping the same controller with everything that entails, like the low level, the feed-forwards, everything, but we adapt the gain using predictive model control, but not any predictive model control. So the one we chose is what we call MPPI, Model Predictive Path Integral Control. It's relatively recent. It has been introduced in 2016. So it's a stochastic sampling-based model predictive control, where basically you sample using a Gaussian distribution many possible trajectories, and then parallelly you have a cost function that can evaluate your progress, the smoothness, the error reduction, anything you want basically, and you will use it not for minimizing purposes, but for scoring purposes. You will basically give a score to each possible trajectory you are sampling, and then based on path integral control theory, there is some kind of weighted averaging that will give you your optimal trajectory that you will apply to your robot. So it's kind of like, it's basically sample-based MPC. So what we did is we didn't actually sample velocity or some other known physical value. We used it only to adapt the gain and to add a small surge bias to help with the convergence speed mostly, and some other issues. So basically what we do is we sample gain values as well as the surge bias, and then we develop our model, which we then score these all these trajectories using the cost functions. So we chose forward progression to avoid backtracking and other issues. We chose to also score based on smoothness, on feature visibility, on feature bounds. And then with the MPPI framework, we apply those gain values and surge add-ons to the same controller we saw before. So we basically pretty much don't change anything except the proportional gain. And then we add a small surge to keep encouraging forward motion in the docking direction. So this is this is primary result for the ideal case without any movement or current. And we can see that the we call it Fast-MPPI-IBVS, by the way, is much faster with very similar performances. And while the performances are similar for the ideal case, it showed later much better smoothness and success rates in perturbed scenarios. So to give a big overview, it has a bigger success rate across all scenarios, and it is much faster in convergence. And of course, the part that interests us is it's more performance in cases where the docking station moves and where currents are applied. It's not shown here, but we tested lots of scenarios: head adverse currents, head assisting currents, lateral currents, cross currents, and the results have been very satisfying. So to conclude, we presented the natural progression of how we're trying to explore pure IBVS-based docking. So visual memory has been a great help for that. And the adaptation layer has also extended the performances. And it kind of encourages the idea I've been trying to defend for my thesis, is that we can do things purely visually. But of course, I'm not stopping there. What I'm currently doing is exploring full visual servoing MPPI, not just for adaptative goals. So I'm trying to explore how to formulate both the sampling, whether it is kinematic, so we sample the twist, or dynamic, where we sample the wrench or the thruster forces. And also how different models, first order, second order, affect performances. So it's my current concern right now. And I'd like to determine which approach is actually more optimal by the end of my thesis. And the reason I'm here is I'd like to validate it experimentally because I think it's really important. I mean, the simulation is quite realistic, but I'd like to, for me, it's important to validate experimentally. Currently, with my supervisor, we're trying to try things with the layer that have been mentioned before in Central. But I think the submeeting could be quite interesting, even just to have like advice and feedback from Claire, sorry, from people. So yeah, thank you. I'm open to. Oh, I have lots of questions. I haven't seen them. Okay. Perhaps if they were asked verbally, that would be nice.
Well, so just a little information about the timing. So we have some, we're completely fine with the time, and even more since we have two presentations which are being cancelled for the second part of the morning. So we can take the time to answer your question, don't worry. And so maybe we'll start by order of people who say they were willing to ask questions. So I think Claire, you're the first one, then Titouan and Morgan.
There was question already in the chat. I think you can also use that because
that's the one I was mentioning for Titouan and Morgan.
I think
if you have Claire first.
I think there is Jalil that was the first.
No, but Claire.
Okay. I can ask my question. So I have. So Nesrine, really congratulations for your presentation.
Thank you.
It's really nice to see your work, and it's a really nice way of doing docking. I have several questions like how many images do you take on the path to go toward your target? And we can see that going from one reference image to another one makes some discontinuities appears. This is something we know about this path of images. Did you think of some solution to remove these discontinuities in the control that we can see on the top right figure? You see that?
Which one?
The top right. So did you think of a solution to remove these discontinuities? And the second related question is, these discontinuities seems to disappear in the Fast-MPPI-IBVS. So my question is, how do you switch from one desired image to the other on this one? Is it smoother or?
So for the first question on how many, you said how many?
I said, did you plan to deal with the discontinuities that are inherent to the method you choose?
So my bet was that predictive control would act like some kind of smoothing filter to deal with the discontinuities. And I also tried to really, how to say, not control, but I structured the cost function, for example, to try to deal with it. So it's been working pretty good. That's the solution. That's how I dealt with it, basically. I don't know if it's clear.
You mean your so it would be nice for me to see when you switch the reference image in the timeline. So it's obvious on the image-based visual-servoing, but it's less obvious in the Fast-MPPI-IBVS. And so did you do a kind of average between the current reference image and the next one, or I don't see how you could smooth this?
Yes, I'm just going to. So, wait, I'm trying to look for it. Okay. Because I'm having kind of some kind of memory betrayal right now.
Maybe if you have your...
I don't actually remember precisely, but for the Fast-MPPI-IBVS, I've implemented some soft constraints that heavily encourage like key point transition. So even though the transition is the same, it's, I mean, for the base schematic, but it doesn't actually remain the same due to the nature of MPPI. That's the main difference between the two. So the MPPI framework actually modifies how we go from a key point to another due to the constraints. But the original one, like my memory is betraying me right now. I'm sorry.
Okay, maybe it would be good to see the cost function over the time, or I don't know. Okay, so
really share my work with you. We haven't.
Feedback scenario. Okay, and
so for MPPI, basically, you can't really enforce hard constraints. You can do it by, for example, for the actuation by clipping and other methods. What you can do is try to shape your outcome through the cost function. So typically, a cost function for such a task is a very, very big one. It's kind of lacks elegance, but it's very practical. So I must have like, I don't know, 12 terms or something in this cost function.
Okay, and the other question is, for your path planning, you need to see the target from the beginning. So what is the difference between a single IBVS? Because you are using the same points, and you just change the reference images, but you could have used from the beginning the last reference images. And what would have been the difference of your robot behavior instead of taking images on the path?
So we made this choice to mostly for exploration. We haven't actually compared directly with a fixed set point. Right now, I'm working like for the things I mentioned, the kinematic and dynamic part. I'm working on fixed set points. I don't have direct comparative results, but we fully believe it is more permissive with the starting position and like different starting positions and different TMS, also motion condition. So especially for the basic IBVS, we think it's more helpful this way. Perhaps the adaptive one doesn't need it, but right now I'm speculating. I haven't actually tried it, but it would be nice to try the comparison for my PhD defense. It's actually a very good question, but yeah, we haven't tried.
Okay, thank you.
Thank you.
So we still have 3 people willing to ask questions. So
yes,
you try not to explode time, please. The 3 of you try to not to make your question too long. So maybe first Titouan. Titouan B. If you can unmute yourself.
I mean, I can also answer by I've had time to read the question by then.
Okay.
So if you mean by structured environment.
Sorry, Nesrine, maybe it's just that I was wondering if maybe Titouan is trying to disconnect and come back. So if you answer and he's not here, that's maybe sad. So maybe we can try to first have Morgan's question, and then when Titouan's back, we'll go back to his question.
Mine will be short anyway.
Cool.
Yeah, I was since you're using visual features and MPC, I was wondering how much that limits the frequency of your controller.
So computational complexity wise?
Yes.
All right. So obviously they don't have the same computational complexity. The IBVS one is fairly linear, while the other one is, I think, quadratic. I don't really remember. What we try to do is indeed keep it very lightweight by only sampling 2 parameters, because generally the sampling is done on at least 6 dimensional vectors. So it was one of the reasons that motivated this approach. But I didn't exactly calculate, I mean, compare like the time and other physical value, like computational values. But for the frequency, it worked perfectly fine by having the upper level control, which is the MPPI, running at, I think, 10 hertz. Yeah, if I remember well. And it works perfectly fine. So, and also there are also some tuning adjustments we can do to reduce the computational load. For example, keeping very short horizons. I think it was 1.5 seconds, and it also worked very fine. So we tried to make it as lightweight as possible, and we didn't have any issues whatsoever. It also ran on very, very, very old hardware, and it was fine. But I didn't explore really seriously, like I didn't calculate and make quantitative comparisons of the computational loads of both. So
thank you very much.
Welcome.
Titouan is saying this micro is not working, so maybe...
Yes, I can read them. So if by
sorry, it's good. I just had to modify some settings in my computer. Sorry. So thank you, Nesrine, for your presentation. I'm also working in underwater docking, so that's quite nice to see your presentation. I had some questions. So what happens if in your simulation, in your gazebo simulation, you had real conditions or real-like conditions such as attenuations or I don't know, unstructured environment? Because for now in IBVS, if I remember well, you are looking for some objects in your scene, and your object is yellow, it's squared. But what happens if you are in a similar real environment, and does it degrade your performance?
So actually, I want to start with, obviously, gazebo is not great for realistic visual effects. So all the degradation, the diffractions, the particles, the turbidity is not well represented in gazebo. So we lose a big part of the realism here. And for simplicity purposes, given that we're basically free on simulation, we chose the planner 4 points that we didn't bother to develop much. But in reality, in our practical setup, what has been working well in literature is very powerful LED light. So you don't just put points or colored edges or whatever. So no, if we were to validate this experimentally, we'd have to have very powerful lighting, and but we haven't done that yet. That's what is missing. My supervisor mostly tried to explore other more realistic simulators, like, I don't know, Stonefish, and I forgot the name of the one that was on Unreal Engine.
Okay.
Hollow Ocean?
Yeah,
And
there is one. Yeah.
like pretty realistic.
Okay.
But they had presented other issues for us that made us stick with Gazebo. So doing kind of advertisement, in last time submitting, I did a presentation of a comparison of a few underwater simulators. You can maybe find it on YouTube, I don't remember. But we searched for simulators, and the conclusion was, stick for Gazebo for now.
Okay. So just to conclude, maybe you can look for self-made simulations on Unity and Rust 2, because you can have some kind of real simulations, and stick with Rust 2. So maybe it's what you will expect if you want to make some real simulation or something like that. But pretty good for your IBVS solution is quite good. So thank you.
I just want to say something about that. Is that for me there is no interest to go for visual-servoing to another kind of simulator, because she will never have something realistic. It's really better that she's working on Gazebo to do the math and the verifications, and then to go in real water, because you can work with Stonefish, whatever you want. You will never have something realistic. So it's better to work from Gazebo and then do something ad hoc for underwater real environments where you will go. And if you are working in a pool, you won't have any trouble to see some lights or some targets. So it's not an issue. And I will skip this step of changing your simulator before the end of your thesis, because you will lose so much time. And going to Unity is not a good advice, because it's really takes time to use it.
Thank you.
I suggest we move to the last question, and then we have the 15 minutes break. So the last question is Alessandro. So,
hi, can you hear me?
Yeah.
Yeah. Hi, Nesrine. Thank you for your presentation. I was curious, mainly because the motivation of your work is because you say that the 3D model, the camera intrinsics, and the calibration is not reliable, but I'm wondering, since we are in a structured environment as a docking scenario in which you know what object you're putting in the water, you can put fiducial marker in the docking station, and you can have a more ground truth reliability on where are you docking and the possible trajectory, if you have compared your type of algorithm with respect to what is done right now with fiducial marker docking station and other type of approaches that has a previous knowledge of the 3D model, which, I mean, I think it's reliable. I don't know. I'm not really into docking, sorry.
So obviously, like all the position-based solution work really well, but that I think there have been some huge engineering work to make them work. And my my position in all of this is that I'm trying to defend. Actually, I'm not saying I'm right, or maybe by the end of my thesis I'll be proved wrong. Is that we can do much simpler, and it's worth trying to explore to do it 100% image-based. And for most of the autonomous docking research, it's been on resident docking stations. So the conditions are much more controlled. And for the one work that did dynamic docking, the engineering work behind it is really huge. There's also some cage motion estimation with fuzzy logic, and there's lots of work behind it. And I'm trying to see if I can do like the same but much simpler. Maybe I'm wrong, but this is research, I guess. We bet on things. But yeah, I wasn't criticizing like previous works. Obviously, they work.
No, yeah, I get that you were trying to find a simpler way to do it without too much engineering. I was just curious on how much can be reliable a pure visual approach when you have a very dynamic environment. Like, I don't know, as soon as you put a docking station in the water, maybe it's get cluttered by fishes and other marine animals. I don't know if the visual memory can fail in that cases.
So there are, I guess, constraints. As long as I haven't tried it experimentally, I'm not foreseeing them yet. I know sometimes people get like crossed by simple things like bubbles and, as you said, fish and stuff, but I'm not there yet. I think I'll think of all of these when I'll be there. For now, I've been mostly concentrating on the theoretical part of my work, and yeah, I think I'll probably cry and panic the day I'm gonna try experiments.
Well, then, good luck with that.
Thank you.
Thank you for your answer.